Hello everyone, I'm Sreekeerthi, a final year dual degree student in Metallurgical and Materials Engineering Department at IIT Madras. In my work, I've done a comparative study of planar capacitive touch sensors with different electrode design structures. Flexible electronics has been gaining a lot of significance in the past few years. Incorporation of properties like bendability and stretchability in the rigid conventional electronic devices largely widens their range of applications as they offer more advantages in terms of their size, their reliability, their ease of fabrication, portability, and energy efficiency. On top of that, flexible devices were also observed to show a better response compared to the conventional ones. Flexible devices can be manufactured through simple routes such as inkjet printing or direct writing techniques. These methods can be used to manufacture devices on large areas and can also be used to fabricate more intricate and complex designs at a low manufacturing cost. Typically, the flexible devices are currently being used in displays, sensors like gas sensing and biosensing applications, RFIDs, thin film transistors, organic LEDs, etc. More specifically, touch sensors play a major role in the modern electronic devices, specifically in the home or industrial appliances. Touch sensors can be of two types, that is the capacitance-based touch sensors and the resistance-based ones. Capacitance-based touch sensors are more preferable because of their high accuracy, sensitivity, and their resistance to the surrounding changes. So how exactly does a planar capacitive touch sensor work? In case of a two-plate parallel electrode capacitor, we have the electric field lines flowing from one electrode to the other perpendicular to the electrode plane. So when we consider a planar capacitor, these electrodes open up, because of which we have two different capacitances in between the two electrodes. Firstly, because of the field lines that are flowing along the electrode plane, and secondly, the field lines that are bent due to the opening up of the electrodes, which causes an electric field called the fringing electric field. It is this fringing electric field that is disturbed when a conducting object is placed in the vicinity of the structure. So for example, if we place a human finger in close vicinity to this capacitor, we can observe that the mutual capacitance between the electrode plates will reduce. That is because of increase in dielectric thickness between the two electrodes, which causes a reduction in the capacitance. While on the other side, due to the presence of an extra conducting object, the self-capacitance of each of these electrodes will increase. However, a planar interdigitated capacitor will give a one-sided access, which means it will show a better sensitivity to human touch compared to other principles such as resistance-based capacitors. So in this work, I've done a simulation-based study of different structures that can be used for capacitive touch sensing, and I've observed how their sensitivity can be improved and which among those structures is more sensitive towards touch sensing using simulations. Here we can see an interdigitated comb-like capacitor structure, which is one of the most prevalent ones among the ones that are being used for capacitive touch sensing. One of the main advantages of a simulation-based study is that we can avoid material wastage and we can obtain easier results fastly without performing any actual experimental work, and these results are also reliable. So I've used PalmSol software to model these three different electrode designs, that is the interdigitated comb-like, square spiral, and block-shaped electrodes, where the electrode design is made of silver and it is present on a PET substrate. Here PDMS acts both as encapsulant and dielectric layer. One of the main reasons of choosing these materials is that PET offers more flexibility, it has high strength, and it is also biocompatible, which means it can be used for biosensing applications. PDMS, on the other side, is a very good insulant and acts as a very good dielectric. Coming to the electrode, usually in experimental fabrication of these devices, we typically use metal nanowires, and among those, silver nanoparticles or silver nanowires were observed to show a large conductivity compared to other metals. So in this case, I have chosen silver to be the electrode material. So how exactly do we model these devices on console? As a first step, we input the device dimensions. In this case, I have fixed the substrate area and I've printed all the different designs appropriately according to the substrate dimensions. For example, here I have chosen the interdigitated comb-like structure with an electrode width and gap of 1 mm according to the substrate area. So once we have modeled the design, we choose the required material for the device. So in this case, we have three different materials, that is the PET layer, the PDMS layer, and the electrode layer. So we divide the whole design into three different parts, that is three different domains, and to each domain, we'll assign the corresponding material which we choose from the COMSOL material library. Once we have assigned the materials, we'll define the ground boundaries and terminal boundaries in the capacitor. That is, we'll define the ground electrodes which are at 0 volt and the terminal electrodes. In this case, I have chosen the terminal voltage to be 1 volt. So, along with the planar study, that is, the study of capacitance variation with geometric parameters in plane condition, I have observed how the capacitance or the sensitivity of this device will vary on the application of a bending force. That is, when I apply a force on two edges of the capacitor, how is its capacitance varying with the amount of force or the amount of bending that is applied. In the first case, where I considered an interdigitated comb-like capacitor, I have observed an increase in capacitance with increasing electrode dimensions. That is, all the three thickness, width, and length of electrodes. This is very evident as we know that with increase in the amount of conducting material in the device, we can observe an increase in capacitance. And here we can see that the capacitance in plane condition for these devices is in the range of 3 to 4 picofarad. Following that, when an edge displacement is applied to the capacitor structure, here this device can be bent in two different directions. One about an axis that is perpendicular to the electrodes, and two about an axis that is along the length of electrodes. In the first case, where the axis is perpendicular to the electrodes, when the structure is bent inwards, we can see that there is no significant variation in capacitance, and in this case, it almost remained a constant in the range of 1.8 picofarad. This can be explained by saying that there is no significant difference in any of the parameters. For example, the gap between the electrodes, they are not significantly changing because of this bending. As a result, we cannot observe any significant change in capacitance. While on the other side, if we bend the structure about an axis along the electrode length, we can observe a significant reduction in the gap between the electrodes, because of which capacitance value was observed to increase from 1.83 to 1.85 picofarad in this case. In case of a square spiral electrode structure, I have observed that similar to the interdigitated comb-like structure, the capacitance value was increasing with electrode dimensions, and with edge displacement, here in both the cases, that is the axis being along the electrodes and perpendicular to the electrodes, the capacitance value was observed to increase, which means we can observe a net reduction in the electrode gap. While in this case, the overall plane state capacitance values are almost 1/3 of the initial interdigitated comb-like structure. Here the capacitance ranges are from 0.8 to 1.5 picofarad. In the third case, where we have modeled a block-shaped electrode structure, the capacitance values were observed to be largely varying from the range of 1.5 to 2.5 picofarad with changing electrode dimensions. But on application of edge displacement, the capacitance values were observed to significantly reduce. That is, they reduced from the range of 2 to 2.5 picofarad to 0.88 picofarad. But on increasing the edge displacement, the capacitance value was observed to increase. So overall, if we compare the values of a square spiral block-shaped and comb-like structure, the comb-like structure was observed to show higher capacitance values, that is a better sensitivity compared to these two structures in both plane and bent conditions. Now, to validate the results that I have obtained using simulations, I have experimentally fabricated the same electrode structures that I have designed to observe how the capacitance is varying. Initially, I've used silver nanoparticle ink that I've printed using an origin direct writing system on a photopaper substrate due to the lack of availability of PET. After heating in an oven, heating it in an oven at 120 degrees centigrade, I've made copper wire contacts using silver epoxy. Now, after that, I've spin coated PDMS on top of the structure and cured it at 120 degrees centigrade for 1 hour. These are the 3 structures that I've printed using the direct writing system. And after that, I've done 2 probe CV measurements to observe how the capacitance is varying with voltage in both plane and bent conditions. Here, we can observe that even though the capacitance values are showing a trend similar to what we have observed, that is, the comb-like structure is showing a better sensitivity compared to square, spiral, or block-shaped electrodes, the capacitance ranges are quite different from those obtained using simulations. Then we can give many reasons for this. For example, the first one, the material that we have chosen in simulations is silver, while in this case, the material that we have used is silver nanoparticles. We know that nanoparticles will show a better conductivity compared to the silver metal, and hence they'll show a higher capacitance. And secondly, we have used photopaper instead of PET, because of which we can observe very slight, but some kind of change in the capacitance can be observed. If we see here, the block-shaped structure capacitance was observed to be significantly low compared to the square spiral one, while in the simulation case, they were observed to be comparable, which means the difference between the capacitance that is obtained in case of block-shaped structure in simulation and the experiment are more comparable compared to the other 2 structures. This can be probably because the structure is not as intricate compared to the other 2 structures. And in case of simulations, we did not have to make so many approximations when compared to the other 2 designs. Now, if we observe how the capacitance is varying with touch, in this case, we can see that that similar to the earlier case, the interdistricated comb-shaped electrode structure was showing a larger capacitance and also a significant variation in capacitance when the device is touched. These are the 2 structures of the interdistricated comb-like structure with bending and without bending that I have fabricated experimentally and measured. Now, finally, I have observed how the capacitance is varying with bending for an IDC comb-shaped structure. In this case, I have observed an opposite trend of decreasing capacitance with the increase in amount of bending. I am still trying to figure out what can be the possible reasons for this difference, but one of the reasons for this can be that with varying thickness of the substrate and encapsulant, the tensile and compressive forces can get reversed, because of which we can observe a total reversal, that is a negative trend in the variation of capacitance, which is in contrast with the simulation results. I'm also trying to follow up this work by applying a bending force on the remaining 2 structures and see how their capacitance is varying with the bending, and also to observe how the capacitance is varying with other geometric parameters. To summarize, I've compared the device capacitance variation with different physical and geometric parameters of the electrodes, and I've observed that the simulation data values are following a similar trends compared to the experimental values. That is, the interdistricated comb-like capacitor was showing a higher capacitance and hence a better sensitivity to touch compared to the other 2 structures. I have validated the simulation results that are obtained with experimental data by printing the same electrode designs using commercial silver nanoparticle ink. In the future work, I would like to use silver nanowires instead of silver nanoparticles to also include the property of transparency, as transparent touch sensors play a very key role in different current modern electronic devices like flexible mobile phones or any flexible displays for that matter. This work was supported under the Institute of Eminence Research Initiative project by IIT Madras. I would like to thank all my lab mates for the constant support in carrying out my project. Thank you very much for this opportunity.